in the car industry. So the first point, just to take a step back, software in cars is nothing particularly new. This is a great ad that Bhuvan dug up from Volkswagen from 1968. And I just love this language. It says, every Volkswagen comes with a computer. It's about 1 foot wide, and it manages the engine control system, the fuel injection system on the vehicle. And then, as we advance, this is some Bosch. Actually, you can see really, like as we get into sort of the late 70s and early 80s, interfacing with chips and computational material on board vehicles. So this is nothing new. So what do we mean? What is new about software-defined vehicles? And based on all of the interviews that we had, it really came down to these 3 different components. So the first component is a kind of centralized architecture. So let me just quickly try to explain this, right? In traditional automobiles, you have a braking system, you have an infotainment system, you have steering system. You would have had individual microprocessors associated with the components in those various systems, right? Which means you could have had 100, 200 chips on a car. And all this is about is saying, let's reduce that number to maybe 4 or 5 different domain areas. That was like a central core of what this definition of software-defined vehicles is. The second part is about these over-the-air updates. So we know what these are now, we're familiar with them, but and as we just heard, every car has a modem on it, so we can actually update the controls on the vehicle. We can offer new features overnight to customers that couldn't be done before because all of those chips would have had to be actually brought into the dealer and the chips like reflashed with different features and functionality. Now that can be done over the air. And then finally, this concept of like constant flow of data, as we just heard on the previous panel, both within the vehicle architecture and connected to the cloud. And so we see this kind of like evolution where on the left in this graphic, this is from Evangelos Simoudas, who I think put together this kind of very nice graphic about the evolution. We started on the left, and now we're in kind of this domain-based architecture. And then moving into zonal-based, and then finally into sort of this future where it's all centralized. But there are some advantages, including even just reducing the amount of wiring inside a vehicle, which can be quite significant. Now, one of our findings is that the legacy OEMs, they've been slow to shift into this kind of new mode of software-defined vehicles moving toward domain and zonal architectures. So you can see some of the traditional manufacturers here. Tesla has already made the transition to a zonal architecture, but some of the other OEMs, still have very few vehicles on offer that really can be fully defined as software-defined vehicles, although they are very much moving in that direction. What are the challenges? Software-defined vehicles we hope will save cost in the long term, but certainly in the short term to get there, there's a big structural cost within the organization. We were actually surprised to hear this one. Lots of concerns about legal, but it makes sense if you think about it. It came up on our panel earlier that, automotive OEMs are really slow. Yes, automotive OEMs are really slow because they have a culture of safety, right? And they have to be in many ways cautious about the products that they offer. And so that, of course, is built into this sort of institutional, I don't want to say legalese, but car companies have lawyers, and they do look at these things, and they do ask questions like, what will we be held liable for? And these are some risky transitions when you're fundamentally rewiring the architecture of the vehicle. Just the complexity of doing this is a big challenge. I mean, you're really rewiring the vehicle, the organizational changes, the cultural changes within car companies, and then understanding sort of the relationship that they've had with their tier one suppliers. We see some of these changes on the semiconductor side as well. So if we think about who makes chips for the automobile, we have these kind of two clusters. We have the legacy players, big companies like Infineon and NXP, and then some newer entrants like NVIDIA, Qualcomm. So this is showing the kind of automotive semiconductor revenue for those legacy players and the new entrants. But if we look at the growth is very, very high for the new entrants compared to the legacy players. And okay, I'm going to wrap this. So the big opportunity here for software-defined vehicles is, to offer sort of new services. And this is really the punchline here. OEMs are very optimistic about offering new services. However, the jury in many ways is out in terms of how OEMs can really monetize this. And so all of this is available in far greater detail in the research briefing, which is on our website. Thank you.
This is work that we've been doing as part of the Mobility Initiative and Michigan Central. So you'll see that the case study that we'll talk about briefly is really focused on the Detroit area. But what motivates this work is really, it seems, I'm in an AeroAstro department as an aerospace engineer. Much of the themes that we're seeing on ground vehicles, we're seeing in the air as well. I think there's a lot of interest in autonomous aircraft at various altitudes, various sizes, and a lot of applications. I should say, since John brought up the history of looking at software on cars, that the first, what we would call robot piloted, so what we would call autonomous today, flight across transatlantic flight actually happened in 1947. So we're all coming up on more than 75 years of trying to make this commercial and consistent reality. Though a lot of the things that we hear about in the press have to do with things like air taxi, the applications that we've been interested in this for this type of technology include things like search and rescue when ground infrastructure is broken, or transport of medical supplies and so on. So that's really what excites us with regard to operating drones. But I think with these new applications that we're really interested in, we should recognize that there are also new concerns and the associated trade-offs between the benefit that we would get from these new services and the impacts that can happen. And in particular, there's a lot more concern about safety of these operations, the privacy implications, both for the people who are possibly the customers of these services, but also people on the ground over whose homes we might have drone operations, and noise implications of these operations. The interesting thing about this space really is that on the regulatory side, it's much more nascent. So the rules are much vaguer in general, although the FAA, when we think about their concepts of operations, there is the objective of supporting safe and equitable access for all users of the national airspace system to either unmanned traffic management services or advanced air mobility services. So some of the challenges that we're trying to address in this project are, what does equitability, what is an equitable service here? How do we measure this? How do we define it? And really, it's equity both in the positive and negative impacts of these services. So last year, I talked a little bit about trying to see how we look at equity in terms of making sure that different regions got balanced access to the services. Today, I'll talk a little bit more about work that we've been doing, looking at the rules that are coming into play on making sure that people aren't impacted, so balancing out the negative impacts of having these, especially low-altitude drone operations. And we also recognize that there are really many categories of users, everybody from the operators, who are the aircraft operators, to the communities who are being served as well. And there are different approaches that we can look at to balancing these these trade-offs between what we would like, the benefits and the risks. Traditionally, we have optimization-based approaches, which would be you have regions that you want to avoid. Don't fly over a school. Don't fly over a playground. So have constraints and then have routing problems. And then what really is the approach that's being taken by regulatory bodies around the world, which is guiding principles and rules. And the most pertinent of which is what the FAA says now, which is a drone operator shall route along major thoroughfares or sparsely occupied areas to the maximum extent practical. So the idea being nudge it towards, let's say, flying over a river or flying over a major road so that you already have noise there or you don't have people under it. And so that is the way that they would like to balance these approaches. So in this work, what we've been looking at really is asking the question, what is the price, the trade-off? So what is the price that we pay when we have such preferential routing? And so the kind of problems we can ask are, let's say that the baseline cost of flying is 1, so it's a unit cost per distance. But if you fly over a river, it's something that's smaller, that's alpha. And so in this example, if you want to fly from the circle to the star, and you would like to preferentially route over those black lines, we can ask, what is the shortest path, which is given in blue, or what is a path that would really minimize the cost, which is get as quickly as possible to the river, fly around the river as much as possible, and then get out to your destination. And really, what we would like to know is what the price of this type of preferential routing would be. So we want to compare this red route, which would be along, try to maximize flying along a river or a major highway against what it would be if we just flew straight line paths. So the case study that we've been looking at is one that's based on emergency response in Detroit, where let's say that we're looking at just current first responder missions in Detroit, with a set of making sure that we are avoiding things like flying over downtown or flying over the airport. We would like to fly over the river. We would like to fly over railroads. And we now ask the question, if you have these a certain number of fire stations where we're going to launch our drone-based rescues from, then what is the impact going to be? So the example, the kind of analysis that we would like to do is try to compare what the blue routes would be, which is for every location where there's an emergency, we'd have a quick response that's based on drone operations, whereas the red would be what would it, and just straight line paths versus what would it be if we actually tried routing as much as possible along the river. And then we can use that to to compare response times, essentially, where we can look at the response times if the current response times here in gray are what we would see with ground-based vehicles. We can compare that to what would it be if we could just fly straight line paths without trying to preferential route, and then what would we get if we had such preferential routing. And really, we notice that there are some regions where this is going to lead to a longer response time, others where it would be a shorter response time, and then that we would then use that to inform a design problem where we can say, okay, what are the right places for us to be able to stage our drone operations from to get balance in these objectives. So that's it, and thank you very much.
Okay. So first of all, just like to thank MI's invitation. Glad to be back. And also just want to take this opportunity to thank our partner agency, Maricopa County Department of Transportation in Arizona, to help us make this happen. So first of all, why are we doing this? As some of you might heard, there has been a growing interest in the use of roadside LiDAR in improving traffic safety and efficiency. States like Tennessee, also Utah, also including Arizona, where I'm from, has been adopting a faster pace in this area. But there are challenges. So basically, essentially, when you have a high resolution LiDAR, the hope is that you can basically feed into the LiDAR data, which is essentially point cloud, into a neural network, and use that, train that neural network for better detecting traffic participants on roads. But not only the object level, we also talk about the transportation perception level, like anomaly detection, predicting average speed, queue length, even detect near misses. So essentially, if you dive into that AI model, there are a whole bunch of neural network architecture people develop. But essentially, if you look at that, the idea is that because the computation on the point level is too expensive, so what people do is they always sort of chunk the 3D space into a whole bunch of grids. Then essentially what you do is you apply neural network to learn features, extract it from each grids. We call it voxel. So the reason why we have this influence by resolution is because the density of point cloud in each voxel will change as you change the resolution. So this is a problem we are facing. Essentially, this is a black box. You wouldn't know exactly how much improvement you gain until you actually put those LiDAR on roads. So that's the dilemma we are facing right now. So to better understand problem and also do a controlled experiment on the influence of LiDAR resolution, we built a testbed in Sun Lake, Arizona. So essentially what we did is we deployed 3 groups of LiDAR with different resolution in the diagonal corners in the intersection in Sun Lake, Arizona. We also include 4 traffic camera, which is what a DOT already had deployed in most of the intersection, so that we can do some comparison. So there are some optimization consideration, which I don't have time diving into. But the idea is really to give a good balanced coverage of not only the central area, but also the area expand from the center. So not only you can detect the conflicts within the center region, but also maybe you can do queue length prediction. In a nutshell, LiDAR, when the resolution reaches a certain level, it outperforms camera near the center area. This especially, in particular, this becomes obvious when it comes to, say, the distance between 40 and 60 meters. But as you increase the distance from the center of the intersection, the LiDAR wouldn't do as much as camera does in terms of detecting traffic, those traffic participants. And there are a couple of contributing factors, including the signal strength of the LiDAR from the detected objects. But according to our study, one of the major contributing factor is actually about a mechanical design. We call it LiDAR beam distribution. Essentially, because most of the LiDAR we build today is still for autonomous driving purposes, it's not originally designed for road sizing purposes. So most of the LiDAR in the market we found right now still didn't optimize for the purpose of have a balanced coverage on roads. So that's one of the things we found as we did this experiment. And if you dive into different categories of different traffic participants, this phenomenon become more and more obvious. If we look at some of the small objects have the smaller size and irregular shapes, such as a motorcycle, bicyclist, pedestrian, or even golf car. And this can be also seen if we look at the statistic from the idea I mentioned earlier, the point cloud densities of different traffic participants with respect to the distance from the center of the intersection. If you can see the like a large size, like a construction vehicle, bus, obviously have a more higher density, but If you look at those irregular size objects like the bicyclist I mentioned earlier, obviously it has a much smaller point cloud density, which is understandable. But those vulnerable road users happen to be be more impacted if you sort of try to reduce the LiDAR resolution, unfortunately. So what we did, as I said, we collect a higher resolution, 3-level resolution LiDAR data, but we also include this 4 camera in 4 direction, and all of them are spatially and temporally synchronized. And we want to, I will try to wrap up shortly. We want to, as a next step, we want to publish this data set for public usage, so other researchers can also benchmark their algorithm in traffic sensing task. This is a pretty, I would say, labor-intensive task. We have more than 20K data frame with all 3D, 2D annotations, and we have a more balanced traffic participants in 10 categories compared to other data set right now we have. And we also have a annotation for trajectory, so you can also sort of use our data set to benchmark some of the spatial reasoning tasks. Looking at the future, we want this to become a more like an open source platform, so other researchers can just leverage our data set for benchmark your AI algorithm in transportation sensing. Also, we want to share those lessons learned shortly in a white paper, which will be available soon. Thank you.
Okay. Thank you.
Set the time for myself as well. Okay, so over the summer, we worked on this report with 3 of our grad students, Chenan, Shinny, and Yunlin, advised by me. Quick primer, Jan 5th, 2025, New York was the first major city in the US to introduce full-scale congestion pricing, south of 60th Street in Manhattan, $9 during the peak hours, 5 a.m. to 9 p.m. on weekdays, and 9 a.m. to 9 p.m. on weekends. They have certain classes and discounts, but I'll not get into that as I have a lot of slides. This report is actually 80 pages long and has 6 chapters. So I'm going to run through this, but yes, we will be releasing this report on our website and in a week or 10 days, and you can access it there. So the first thing, obviously, everybody's asking, what about traffic and congestion? So all the data we looked at in this report is from Jan 2025 to June 2025, a good 6-month period, and we compared it to the same period last year, 2024, and in some cases even 2023 as a control. We used various sources so that we're not looking only at one source. So we looked at Replica for synthetic population data and travel patterns, TomTom for real-time traffic flow, Google Maps, and New York City DOT's traffic speed counter data for travel speed. So trips, so CRZ is congestion relief zone, which is basically Manhattan below 60th Street, anything south of Central Park. So private auto trips into the CRZ have reduced. We've seen a peak reduction of up to 26%, but you can see in May and June, this has been tapering off. And this is a theme you'll start hearing constantly. So even here, these are the cumulative trips, and May, June, April, you can see the effects are tapering off. Trips within the CRZ, it's actually started spiking after April. We've seen it's going up, and on a cumulative basis, these trips are actually up 7% in total. Trips outside the CRZ don't seem to have been impacted by the congestion theme much, and they seem to be at a higher level all through 2025 versus 2024. And this is the cumulative version. But the good news is within the congestion relief zone, speeds are up by around 5%. Though again, in the June and July period, you can see that the difference between the orange and the gray line is getting closer. So the benefits seem to be tapering off. And the travel time is down by 4.4%. Same thing again, differences is tapering off. Congestion level around, this is the FDR driveway around Manhattan. It was lower in the first 5 months, but seems to be back to normal by the end of June. And this is overall congestion for Jan to June, every day, daily congestion. And it's, I think there was a good impact for the first 4 months, but it seems to have tapered off by the end of June. The same story if you look at specific road segments. The orange line and the gray line seem to be meeting around May, June. And so that's an interesting story. We also looked at honking complaints. And it's a proxy for congestion, right? You're more frustrated, you keep honking. So overall, they are down, though there's some, some spatial heterogeneity, but it's come down. But again, they seem to be, the benefits seem to have tapered off. Okay, so car travel overall slightly down, but benefits tapering off. What if we move to public transport and biking? So we looked at all these, the 5 boroughs, all the stations, all the bus routes, all the subway routes. And what we saw is, first, bus ridership. Bus ridership is up by 14%, great. This is across all the 5 boroughs. If you split it by inside the zone, partially inside the zone, that is crossing, and outside, it's still a good increase. You're seeing 20% increase inside the zone, and even outside the zone, as in the Bronx and all, we're seeing a good increase. This is a great slide. If you look at the bottom, we see the AM and PM peaks. The orange peaks are really gone up. So people are actually using the bus more to commute. So that's a good sign that they're not driving. New York anyway, like 55% of the folks use public transit to get to work. So this is a good sign. Similar story with subway, maybe not as much as bus, but a healthy 8% increase across the 5 boroughs. And if you split it, it's a similar, it's a good story everywhere. And by day of week, weekdays see the biggest increase, weekends not as much, which makes sense. City bike ridership, John mentioned this as a trend. A healthy 17.3% increase, despite the stations growing only 4%. I think this makes sense because folks, hey, there's this new congestion fee. Instead of buying a new expensive e-bike, maybe I'll try using a city bike and biking to work. And day of week, the increase is most during the weekdays and not so much during the weekends. These are NYC's bike counters. We looked at all the bike counters. The increase is much lesser. It's around 3%. And we attribute this because the most Midtown Manhattan and the Upper East Side don't have bike counters. So the spatial representation is not as good as city bike. Plus, you're more likely to use a city bike first before investing in an expensive e-bike. Okay, I'm going to run through this. We actually used a Bayesian multinomial logic model to see if we could look at an actual shift of folks from car to transit. And we could explain some of it through this model. Auto trips were down by 5.3%, and public transit trips up by 1%, and the relative share changed 1.2%. So, and this was trips to the congestion relief zone. Within this congestion relief zone, auto trips actually went up. So maybe because of the lesser congestion, people who stay within the congestion relief zone were driving a little more. But even public transit trips were up. So I think everybody is just enjoying New York much more. This is one important one I just wanted to highlight. We have much more in the report. That lower income segment shows smaller shifts and auto trip reduction. They are more sensitive. These are trips that they have to take to work, for education, or the hospital. I'm going to skip this, but the TLDR was basically, despite economic volatility, tariffs and all, employment remained stable, earnings remained stable, office attendance rates remain stable, work from home remains stable, business revenues remain stable across sectors. Visitation was down, but revenue remained stable, so you're getting more meaningful customers. I don't know what that means. Residential property showing the normal seasonal fluctuation. Office property was a stellar performer with 42.2% increase in, I think, leasing. So that's the summary. Thank you. We'll release the report soon. You can have a look, and we'll have some recommendations on it. Yeah.
Okay. I just want to say.
In this next one.
Yeah, and you're on to the next one. So here we're collaborating with Gensler, which is the world's largest architectural and design firm. They've been wonderful partners of ours at the Mobility Initiative, and this is a project on the carbon footprint of a Workday.
Okay, so why did we look at this? Because building operations and transportation emissions represent more than half of global carbon emissions. And Gensler obviously is an expert in the built environment, and I think we know some stuff in the transportation environment. So let's do this. Residential space in the US is the majority of the built environment in our cities, with single-family homes in most US cities occupying more than 50% of the space. So we actually collaborated on this work. We did some of the commute calculations. Gensler did the home and office carbon calculations, and then we came together and made this calculator, which is available for public access. shouldn't come as a surprise to most folks. Single-family homes are more carbon intensive per person than multifamily homes. And offices are much more carbon efficient because in an office, you typically use 150 square foot if you have a desk. In a home, if for the per person in a household, it's around 650. We actually use the actual numbers of this average multifamily, single-family home divided by the household size, but these are good averages to go by. If we move to the actual carbon intensity now, dirtier grids like Chicago have a much higher carbon intensity. California is a very clean grid, so the CO2 emitted per square foot per year is much lesser. But how can you actually reduce carbon further from your home is by implementing setbacks. And a mild setback is what we say, minus 30%, setting your cooling to 80 and heating to 67 when you leave the house. Aggressive is probably turning it off. But obviously, everybody cannot set back. So this is from a Gensler survey, and around 50%, depending on the city, is how many people can actually set back their thermostat. So what does all this mean? Sorry, I have to cover the commute bit. US is primarily everybody drives alone to work. Percentage of people carpooling has come down. Public transit has suffered since COVID and is around 80%, 75 to 80%. Cars are nationally dominant, but in cities like New York, close to 60% take public transit. What does this mean? Public transit is more carbon efficient than a gas car or even an EV in most cases. Bike share, because of the rebalancing and using vans, has some carbon impact, and we assume that biking and walking, using your own bike, is zero carbon, operational. Some good insights that came out when we were doing this research is commute distances are much shorter in transit-rich cities. That makes sense. These are older cities, much more dense, and you have good commute connections, so people stay around these stations. And walking and biking is inversely correlated with car commute. So obviously, because the city is more spread out, there's less propensity for you to walk or bike, and you'll probably drive to work. So when we put all this together, we actually used 4 scenarios. One is, hey, you're working from the office, you're not setting back your home, you're not touching anything there. You're working from the office, you're doing a mild home setback. You're working from the office with an aggressive home setback. You're working from the home, but the office is still there. The office doesn't disappear, right? So we looked at different cities. New York is very transit-rich, so even if you set back slightly and you're taking the train to work like most New Yorkers do, it's way more efficient to just go to work because you occupy less space there. Office buildings are more modern, more efficient, so the amount of carbon you consume, operational carbon per workday is much lesser in scenario 3. Houston, it's very spread out, it's sprawling. Avoiding gas car commutes is the most effective way. So either like EV carpooling, or if you can work from home but not have the office, that will be great if that's possible. California has a clean grid. San Francisco is a compact city with decent transit, so it keeps emissions low in all scenarios. And I think LA is like a great example of how you can move to EVs because the grid is clean. The home and office emissions are lower, so it's only the long commute that actually is generating carbon. So if you actually move to an EV, you reduce your carbon by a big margin. Some key takeaways. We must leverage shared infrastructure to reduce workday carbon emissions. Multifamily homes are more efficient, office spaces are more efficient workspaces than home, and public transit is more efficient than driving. I think we need to continue decarbonizing the grid and weatherizing homes. In places like Chicago, the coal usage needs to come down, homes need to be more weatherized. And I think because the same lifestyle in Chicago versus San Francisco, more than twice the carbon emissions. Setbacks helps maximize savings, and it's not possible that for everybody sets back, but where possible, one should always choose to set back. And US there are a lot of cities in the US that actually have long commutes. I know it's not possible for everybody to choose public transit, but EVs, carpooling, and if you can move to a neighborhood which has some light rail transit or a bus, that can actually reduce your weekday carbon emissions by a big extent. But we know that all of this is, it doesn't, match with your particular scenario. So we actually made this personal calculator with 9 US cities. You can play around with different scenarios and simulate like, hey, if I move from a gas car to an EV, or if I move from my 2,000 square foot house to a 1,500 square foot apartment, how does it change if I got a heat pump versus electric heating? It's live on our website. You can actually go there. Only tip is don't use your mobile phone because it's a very wide dashboard, so use your laptop. I actually think I did this with 20 seconds to spare. Thank you. And
slides here. Gensler, where he already introduced us. We have a research institute. We pour some of our profits into research across all of our sectors. And we're going to be talking quickly about user experience across transit modes. I'm going to introduce this, skip through a lot of stuff in public transportation and get to recharging because there was a lot of chat about that today. So we've done all this research in this kind of REACH program, and it started with SFO. When we opened up SFO Terminal 2, which we designed, the airport told us they were making more money per passenger than any airport in the country, probably in the world. They didn't know what we did. They said, we want you to bottle it because we want to bring this forward to all of our other terminals. And what we did, we developed a set of design guidelines titled REACH, which stood for Revenue Enhancement and Customer Hospitality. We're a design firm. We think about human experience. We think about the human first. We design things from the inside out. And essentially what we did was pretty simple. We broke up the journey into a series of journey moments, arriving at the airport, ticketing, going through security, et cetera, and using a qualitative research where we broke up those different user typologies, tourists, business travelers, et cetera, and we tried to understand what their emotional journey was through each one of those points, and then we made design interventions to support them in their emotional journey through the airport. Turns out when people are taken care of in that way, they spend more at the retail. So let's go on to transit. So we're really interested in the transportation practice. How do we bring this thinking into the public transportation systems where they don't care about revenue, but they do care about ridership? So we're able to keep the same acronym. So we just created REACH for transit, which is rider experience and customer hospitality. So essentially our research question was, how is the experience of public transit changing post-COVID? What factors have the greatest impact on experience, and how can design enhance it? So we used the same methodology, broke up rider typologies, sometimes riders, daily riders, used to be riders, dependent riders, and broke it into journey moments and talked to them. And we talked to them across 3 systems, LA, DC, and Atlanta. We had different typologies. I'm going to rip through this pretty quickly. Different transit moments. You can imagine what they are, ticketing, waiting on the platform, riding the train. And here's some insights. Safety first. Aha. People need to feel safe and secure when they're riding the system. Keep it clean. These are civic spaces, but we have to double down and keep these places clean. Free time matters. People are on their phones now. You can't be on your phone when you're driving your car. People appreciate this. We need to lean into that as an insight. People talked about it. Ease of use and environmental comfort are essential. And people make the difference. The people you're riding with and the people you see in the stations. Are you seeing, armed guards with flak jackets and machine guns, or are you seeing hospitality folks with bright colored jackets and smile on their faces with maps to give you? So the conclusion is potential transit riders have more mobility choices than ever, including virtual mobility, where we don't even go to point B, we just kind of do that virtually. Experience matters more. So we need to improve the ridership experience by focusing on safety and security, ease of use, and community pride as the best ways to start. And here's a picture of a rendering. We're redoing LA Metro's legacy stations, and if I had a before picture, I can tell you it's a dark and scary place, and we use a lot of design moves to fix this. Now, recharge. Okay, so we're stretching the reach, but it's the same thing. It's about charging. It's about charging stations, the experience there. So what is the experience of EV charging today? How can we design interventions that improve that experience? How can we how can better charging infrastructure support a range of sustainable transportation options, et cetera, et cetera? We know that half the people through other research we've done are unwilling or unable to buy EVs right now. So that's part of it, and charging is a big factor. So the same process. We did a lot of secondary research. We did primary research where we met with user groups, and we synthesized that and created some kind of insights that we're taking forward in the design of next generation charging stations. We looked at 2 markets, Toronto and LA. We wanted to look at London and Mexico City as well, but we'll wait till the next round of funding comes in to do that. So focus groups, the experience moments included planning your trip, parking, connecting, charging, and then driving off. The profiles were electric commuters, urban chargers, EV road trippers, and gig workers. So ease of use. What was interesting in Toronto and in LA, there was kind of different insights. Insights included, well, just generally speaking amongst both cities, to summarize, the charging experience right now sucks. You know, people have to find, they're hard to find. They're using all different kinds of apps to find the charging stations. They're in the back of car dealerships. Sometimes you get there, they don't work. They're scary, they're dark, there's no attendant there. I mean, it's basic stuff. They get in there and they're charging for 20, 30, 40 minutes, and there's nothing to do, there's nothing to buy. There's not even a trash can. It was like the simple stuff. I think ultimately, there's a lot of work to do on the design of these systems to make them memorable. Everybody said they hated the charging experience and they avoid it in the wild. They avoid it at all costs, and essentially they all charge at home. A lot of people also said, just in conclusion, that even though they had an EV today and they loved it in many ways, if it was just about the charging in the wild experience, they wouldn't buy another EV, or at least they would go to a hybrid. So it's a big deal. Thank you very much.
Thank you.
I don't know whether you had enough of slides today, so I thought we're going to show you a little bit the hardware on which EV hopefully one day will drive. I'm also one of those EV car owners who have only one fear when they get in the car is, will I have enough soup to get to the next charging station? But where I'm coming from actually is something completely different. Think about concrete is everywhere in our infrastructure, and but concrete, of course, has nothing to do with charging a car. It has only to do with the strength and with the hope that there are not too many holes in the street. However, when you mix cement, so the binding phase of the powder, which gives you the binding phase of concrete, together with carbon black, so a refined form of charcoal, water, and superplasticizer just to make it work. Well, what you're able to create is actually an electron conductive material, a little bit like a stove. In fact, the first application of that material, electron conductive material, actually were in self-heating. We developed that during COVID, where we wanted all to eat outside. You remember when the heat came from above, but your feet were always cold. So we wanted to have something which heats it. So that was the first application. We have now tested that here in Sapporo over the last winter, and we're now in discussions whether this can be implemented for the entire city of Sapporo. But more generally, you could use this also for runways, tarmacs, etc., if they are running, and hopefully the government will open again, right? But then, once you have an electron conductive material, you can actually store energy. And my talk was entitled, We Talk About Batteries. So I want you to make sure, I want that you all know, I'm not doing batteries. What I'm doing is actually supercapacitor. The difference between the two, every engineer should understand. I didn't know it 6 months ago. So is a battery takes electrical energy, turns it into chemical energy, and backwards. That's why your efficiency of your battery goes down. A supercapacitors, is what you have in the car when you brake, and where the energy is stored in EV car is intermittently stored, and then it is stored into the battery. It keeps electrical energy. So we started out with a couple of those systems here, and if I get this here, so you see on the left side, these were very small electrodes made out of this cement carbon material. 3 were enough to get an LED. Then we start building bridges. I'm a bridge engineer by hope, but never made it to MIT only. And then we were building energy capacity. And I asked actually one of Moini to bring one of our super cups here. So you see here how it works. Yeah, turn it on. So you see it runs a fan. So you have here a little bit this large-scale Oreo design. electrode, positive, negative charge, and then you have here 12-volt battery. And then for those of us who are a little bit older and who still remember these things, gameplay, you can put them in here. So there's no battery there, so there's not cheating here. Who would like to play now? No? Okay. Well, anyway, but what you see here in essence is, in action, energy storage in concrete materials. And once you have this here, you can actually think about how we can use that. Well, right now what we're doing, we're having these column type structures on the right side. So that's a 0.25 cube meter concrete column filled in. That is soon enough. So double that size is enough for a fridge. So that goes into homes, of course. But what we want to get to is self-charging roads. And the one thing which I have here, and now I hope that I will be able to get this video going, if it is still there. Can you try? So the first thing is you can use these type of supercaps. Yes, you can try them. If you can switch off just the tone, you can switch off the. You can use them actually to transfer energy for self-charging roads. So the principle of self-charging road is very similar to how you charge your phone wirelessly by electromagnetic induction. What you need to create is an electric field, and that electric field is then transferred by means of magnetism from one side to the other. In the car, you have a coil. In the road, you have a coil. That's technology that already exists, but you can use that material here in the system. So the first trial, of course, goes always wrong in the lab. Then he calls finally a student for help. I said, please put it on it, right? So the student knows, let's say that you have two cables, positive, negative, right? And it goes on, okay. So that is as an energy source here. But ultimately the goal, of course, is that the road itself creates, rather than a coil, which are not stable in roads for a long time, these copper coils, is actually to use the geometry of the roads in order to create these electric fields, which are then able to transmit wirelessly the charge to the top. I don't have yet the results for it, but our estimates is that that would increase the battery by about 20 to 25% maximum, given the conductivity of the material. And I'm always the unlucky one who has not the hand on the 6 minutes, right? But what I want to, my point here is, we hope that soon we can actually get rid of this fear of driving EVs and just thinking about where to charge by getting this extra mileage out of the roads, not only for strength, but for charging of electrical vehicles. Thank you very much.
Okay, this is a